Hi everyone. Today we're going to continue our discussion on acids and bases. And last time we were discussing the Arrhenius theory, which defined acids and bases. Today we're going to discuss the Brønsted-Lowry theory, which has a more widely applicable definition of acids and bases. So in this case, we're going to consider any reaction that involves proton or hydrogen ion transfer from one molecule to another as an acid-base reaction. So this will be regardless of whether it occurs in aqueous solution or if there is hydroxide ions present. So you'll notice that next to the hydrogen ion, I put the term proton. And remember that hydrogen atoms contain one proton and one electron. But if a hydrogen atom loses that electron to become an ion, all that's left is one proton. So we can use the terms hydrogen ion and proton interchangeably. Now, additionally, the Brønsted-Lowry theory really does expand upon the Arrhenius theory. There are some cases where the Arrhenius theory doesn't quite hold up. So all reactions that fit the Arrhenius definition, they do also fit the Brønsted-Lowry definition, but the reverse is not true. So not all Brønsted-Lowry acids and bases will fall under the Arrhenius definition of acids and bases. So all that really means is that the Brønsted-Lowry theory just expands upon the Arrhenius theory. So according to the Brønsted-Lowry theory, the acid is a proton donor and the base is a proton acceptor. So we're going to see a proton transfer between two molecules, and the molecule that gives up a proton or hydrogen ion is the acid, and the molecule that accepts the hydrogen ion or takes the hydrogen ion is the base. Now there's also a little note here that the base must contain an atom with an unshared pair of electrons. So a lone pair of electrons. So down below we have a generic reaction between an acid and a base. And the acid is shown as a capital A with a hydrogen attached. So that A could be anything really, as long as there's a hydrogen attached. And then the base is represented with a B, and it has a lone pair of electrons. So now let's show what happens between this acid and base. We're going to draw something called an arrow pushing mechanism. So the lone pair of electrons on the base is going to accept or grab onto that hydrogen on the acid. And that's going to give us one of our products. So B will now have a covalent bond with that hydrogen. And because the base has accepted a hydrogen ion, initially it was neutral, but now it will have a positive charge. And then the acid, after it loses its hydrogen, is going to keep the electrons that were in the covalent bond. So now we get our other product, which is the acid, but this time it has a lone pair of electrons, which was the covalent electrons, and it now has a negative charge. So let's look at an actual example between an acid and a base. So in the last video, we saw that hydrochloric acid can dissolve in water. And when that occurs, hydrochloric acid will transfer its hydrogen to water. and as a result, we'll end up with a hydronium ion. So again, hydrochloric acid is the acid, it's in the name, and water is going to act as a base. So I'm going to draw the Lewis structures of each of these molecules. And we're going to draw that same arrow pushing mechanism. So one of the lone pairs from our base, which in this case is water, is going to accept or grab onto the hydrogen from the acid. And then the electrons that are in the covalent bond between hydrogen and chlorine is going to, those electrons are going to stay with chlorine. So now we end up with our two products. So our first product is the chloride ion. So remember that chlorine usually has 7 valence electrons, but now we've added one more electron to give chlorine an octet of electrons. So chlorine now has a negative charge because it has one more electron. The hydronium ion has an oxygen bonded to 3 hydrogens, and then that oxygen also has a lone pair of electrons. And we can use our formal charge calculation to determine where that positive charge exists. Does it exist on the oxygen or on one of the hydrogens? So each of the hydrogens have 1 valence electron. And then if we subtract any lone pair electrons and then half of any of the bonded electrons, we would find that each of the hydrogen atoms have a formal charge of 0. So the positive charge must be on oxygen, but let's just double check. So oxygen typically, or always, has 6 valence electrons. And then we're going to subtract the 2 lone pair electrons. And then we're going to subtract half of the bonded electrons. So that's 6. So we've got 2, 4, and 6 bonded electrons. So 6 minus 2 is 4. And then we're subtracting 3. So that would give us a formal charge of +1 on oxygen. Okay, great. So now let's look at another example of an acid and base reaction. So this time we're going to look at a base, ammonia. And ammonia, or NH3, dissolves in water, and it accepts a hydrogen ion or proton from water. So we end up forming the hydroxide ion as one of our products. So in this case, because NH3 is our base, water is going to act as the acid. So let's draw the Lewis structures for these molecules. And we're going to draw an arrow pushing mechanism again. But this time, NH3 is the base. So its lone pair of electrons is going to grab onto a hydrogen, this time from water. And then the electrons between hydrogen and oxygen are going to stay with oxygen. Now you'll notice that I drew double arrows here, and that's because this is a reversible reaction. So this goes back to our discussions on equilibrium from chapter 15. So that's from Chem 162. So our two products here, we're going to end up with the ammonium ion, where nitrogen is bonded to 4 hydrogens, and then there's a positive charge. And then our other product is the hydroxide ion, which has a negative charge. Okay, so let's double check where those positive and negative charges are within each ion. So we're going to use our formal charge calculation again. Now, in both cases, each hydrogen has a formal charge of 0 again. So let's just double check that those charges actually exist on nitrogen and oxygen. So focusing on the ammonium ion, nitrogen has 5 valence electrons. And then in this molecule, we don't have any lone pair electrons, so we're going to subtract 0. And then we're going to subtract half of the bonded electrons, which is 8. So really we're subtracting 4 from 5, so we get positive 1 on nitrogen. And then in the hydroxide ion, we're going to focus on oxygen. Oxygen again has 6 valence electrons. And then in this molecule, there are 6 lone pair electrons. And then we're subtracting half of the 2 bonded electrons. So 6 minus 6 is 0, and then minus 1 gives us negative 1 on oxygen. All right, so that's just a little refresher on formal charge. The main message here, though, is the acid and base reaction. We're transferring a hydrogen between the acid and the base. So you probably noticed that water acted as an acid in the first reaction, or in the second reaction, and it acted as a base in the first reaction. So water is what we call an amphoteric substance. It can act as either an acid or a base, and that's because it has both a transferable hydrogen and an atom with lone pair electrons. So if we draw the Lewis structure again, we can see that it has 2 lone pairs and 2 hydrogens. So it can act as an acid or a base. So again, in that first reaction we went over, water was acting as a base because it was in the presence of an acid. And then in the second reaction, water was acting as an acid because it was in the presence of a base. And there are other examples of amphoteric substances, but water is the main or best example. Now, one of the advantages of Brønsted-Lowry theory is that it illustrates reversible reactions. So we did see a reversible reaction between ammonia and water, but let's look at our generic acid-base reaction from earlier. So here we have our acid and our base, and we produced 2 products from that reaction, one with a negative charge and one with a positive charge. Now, what if we flipped the reaction so that the products were actually the reactants? So if we were to focus on these 2 molecules, or these 2 ions, which one would be the acid and which one would be the base? Well, on the left, we have something with a lone pair of electrons, but it doesn't have any hydrogens. So that would be our base. And on the right, we have something that doesn't have any lone pairs, but it does have a hydrogen. So that would be the acid. And then if those two react, we end up with our original acid and our original base. So the original base, which was B with a lone pair, that has an extra hydrogen after the reaction, so it will act as an acid in the reverse process. And then the original acid has a lone pair of electrons after the reaction, so it will act as a base in the reverse process. And that's why these reactions can go back and forth, as long as you don't have, for instance, a strong acid, which is going to completely ionize, and it's not going to go in the reverse direction. If you do have an acid or a base that can produce products that will go in the reverse direction, then these two things that we went over are true. All right, so let's look at that reaction between ammonia and water because that was a reversible reaction. So initially we had ammonia, NH3, which was our base, and water was acting as an acid. So if we look at the products, we can see that the ammonium ion has an extra hydrogen. And if we draw the Lewis structure again, we can see that nitrogen does not have any lone pairs, so it cannot act as a base in the reverse direction. So it would be our acid. And then the hydroxide ion would be our base. So in this instance, we can start to pair up our reactants with one of the products. So NH3 would pair up with NH4. And we're going to call that a conjugate pair. So the base is becoming an acid in the products, and we would call that product a conjugate acid. And then the acid, we can pair up with the product that is a base, or the hydroxide ion in this case. So the acid and its conjugate base are a pair. So now if we look at those conjugate pairs, you'll notice that NH3, which was in our reactants, has gained a hydrogen and become the ammonium ion. So initially we had 3 hydrogens, and then we gained a hydrogen, and now we have 4 hydrogens. And then our acid, water, lost a hydrogen and became the hydroxide ion, or the conjugate base. So one way that you can identify conjugate acid-base pairs is by looking at the difference in hydrogens. So for our acid and base pair on the right, initially we had 2 hydrogens, and then at the end we had 1. Okay, so let's go over an example. And this is from your worksheet for Chapter 16. So if you have access to a printer, feel free to print that worksheet. Otherwise, feel free to write this down in your notebook or follow along with the video. So in Worksheet Problem 1, we are asked to identify the Brønsted-Lowry acid, the Brønsted-Lowry base, the conjugate acid, and the conjugate base for each of the following reactions. So let's go over the first one together. I'll choose blue here. So in the first reaction, we have a binary acid, hydroiodic acid, and water. And this is partly why it's important to know the common acids and bases, as well as how to name acids and bases, because it will help you recognize what is an acid, what is a base, and that will help you for cases like this. Okay, so we've identified our acid, and remember that water is an amphoteric substance, so it can act as an acid or a base depending on the situation. So in this case, because water is in the presence of an acid, it is going to act as a base. Okay, so those are our Brønsted-Lowry acids and bases for this particular reaction. And then we're going to identify the conjugate acid and the conjugate base in the products. So I'm going to use a different color. Let's use red. All right, so in our products, we have the hydronium ion and then the iodide ion. So we can probably tell right away that we want to pair up HI and I. So those look like they kind of go together, right? So HI has lost a hydrogen, so we'll write minus H plus there. So when the acid loses a hydrogen, it becomes a base. So I minus would be the conjugate base. Okay, and then we can also pair up water and H3O plus. So in this case, water gained a hydrogen, so we'll write plus H plus. So that means that the hydronium ion is our conjugate acid. Okay, so now I want you to try this on your own, so you can pause the video and try working through B, C, and D, and then when you're ready, you can restart the video and we'll go over the other three together. Okay, so I'm going to erase and make more room here for the other three. So for B, let's identify the acid and the base. Okay, so we have CH3NH2 and water. So this one, it might be kind of hard to tell which one is the acid and which one is the base. So maybe what we'll do in this case is we'll start by pairing up the reactants with the products. And maybe then we'll be able to tell which is which. Okay, so it kind of looks like this first reactant would pair up with the first product. They look pretty similar. The only difference is the number of hydrogens attached to nitrogen. So it looks like the reactant gained a hydrogen. So that must mean that this reactant is a base because it accepted a hydrogen. Now that would also mean that in the products, its pair is a conjugate acid. So in the reverse reaction, the first product would act as an acid. All right, so now for the other reactant, which is water, because it's in the presence of a base, it's going to act as an acid. And then it's going to lose a hydrogen and become the conjugate base. So we'll write minus H plus there. Okay, so we've identified the Brønsted-Lowry acid, the Brønsted-Lowry base, the conjugate acid, and the conjugate base. And this one was a little trickier, so we started by pairing up the reactants with the products first, and that helped us identify which reactant was the base and which one was the acid. Okay, so I'm going to erase this, and we'll move on to C. Okay, so for part C, this one is maybe a little easier to identify. We can see that in the first reactant, we don't have any hydrogens. So it can't act as an acid. It doesn't have any hydrogens to donate. So that would be our base, which must mean that water is acting as an acid. So now let's pair up each reactant with a product. So the carbonate reactant, CO3 2-, that should pair up with the only product that has a carbon in it. And we can see that that reactant gained a hydrogen. So the product would be the conjugate acid. Okay, and then water, again, pairs up with OH-. And because water is acting as an acid, it's going to lose a hydrogen, and the product will be the conjugate base. Okay. So now let's go on to D. So I'm going to erase my work on part C. And of course, one nice thing about these videos is you can always pause if I'm going too fast. You know, feel free to pause the video and take notes if you need to. Okay, so the last one, D. This one's also a little easier. We have hydrobromic acid and water. So HBr is the acid, and that must mean that water is the base. And if we look at our products, HBr should pair with the bromide ion. And we've lost a hydrogen in this case. And so the product would be the conjugate base. And then water pairs up with the hydronium ion in the products. And in this case, because water is the base, it gains a hydrogen. So the hydronium ion would be the conjugate acid. Okay, so that's the end of our discussion for this video. In the next video, we'll start discussing acid-base strength. So how do we tell if an acid is strong or weak? How do we tell if a base is strong or weak? So we'll go over more of that in the next video.